Okay, in this screencast, we're going to look at applications of arithmetic and geometric series, how they can be used in answering context-style questions. Now, before we get stuck into a couple of examples, which I've pulled straight out of the textbook, but they're good examples. Let's just recap what exponential growth is. And the formula that you might have seen for compound interest, but it describes it's the equation that describes any sort of exponential growth or decay, decay, reduction, growth, increase, which is really just determined by this sign here. If it's decay, that's minus. So we've got a starting amount here, P. 1 plus r over 100. Now, r represents the rate of growth as a percentage. So if it's 20%, r is 20. This would read 1.2. N's the number of compounding periods. Might be yearly, might be monthly, might be daily, might be minutely. So this is our model for exponential growth. And if let's see if I can bring up a little Desmos. Oh, hang on. Yeah, a little Desmos graph of it. So this is where R is set. This is a starting amount of 10, and R is set at 2.4% at the moment. So you can see as R increases, we get steeper and steeper. So for a starting value of 10, after 100 compounding periods, we are now at a value of 200. So it's 20-fold increase over 100 compounding periods. Now that could be 100 minutes, could be 100 months, 100 years, just depends. Okay, so that's the idea. There's the exponential growth graph, and we've been talking a little bit about such curves, haven't we, in the last few months. Okay, let's have a look at this example here. The number of Facebook users at the end of 2008 was 145 million. This is an example with some big numbers in it, growing at a rate of 3% per week. At that stage, at the end of 2008, it was the number of growers, the number of users was growing at a rate of 3% per week, right? So this N is a per week thing. At the end of 2010, the number of Facebook users was 608 million, started at 145 million. It's not a bad idea when you're doing a test to do this sort of thing. It's just to pull out the important things, the important features. End of 2010, from the end of 2008. So that's a 2-year period. All right. If the rate of growth had remained constant at 3% per week, determine the number of users at the end of 2010. Now, this is a little confusing because we're told the number of users is 608 million, but this is not an amount that was arrived at with a 3% per week increase over that 2 years. So what this question is saying is, if it had increased at 3% per week for that 2 years, what would the final amount have been? Right. So we're starting with one. So we're going to use this compound interest, that this exponential growth formula, to come up with our answer here. So we've got 2 years, right? So we've got 2 years, but it's 3% per week, right? So that means that's what have we got? 52 weeks a year. That's 104 weeks, right? So that means that N is equal to 104. Okay, R is equal to 3%. And what else do we need to know? Oh, P is equal to our starting amount, which was 145 million. All right, 145 million. Righto. Now, if the rate of growth had increased, so all right. So this means that part A, the amount that the number of Facebook people after 2 years would have grown from 145 million to, right, so 1.03 goes inside my bracket. It's a 3% growth per week. So there's 104 weeks in my 2 years. Okay, so this goes through. This is going to be an enormous figure. Let's have a little calculate here. We'll hang on a sec, we better get the calculator out. And what do we have? So we had 145, 1, 2, 3, 4, 5, 6 times, what do we think? 1.03 to the power of 104. Okay, 3.14 times 10 to the power of 9 is what that says. 3.14 by... Right, so this answer is 3.14 times 10 to the power of 9. Now, 10 to the power of 9 is billion. So 3.14, so roughly 3.14 billion users if it had stayed at the 3% per week. So clearly it had dropped because 608 million were using. 3.14 billion would have been if the rate of 3% per week had stayed. Okay, the growth rate of 3% per week remained steady for 6 months. Okay, so this was actually the case. And then it dropped to 1.1% per week, and that was for another 6 months. Then it dropped to 0.75% per week. So that would have been, assuming this rate was sustained for a whole year, show that this model better describes the record numbers. So I imagine that through this, we'll get closer to the 608 million. So part B is going to be a multi-stage event. So 3% for 6 months. So we started with 145. So, all right, so our amount goes 145 million by 1.03 for 6 months, which is how many weeks? 26. Right. Now we'll take that amount. Maybe we'll just figure out what that is. Get out our calculators. All right, I'll pause for this. Okay, so we can see here that the calculation comes to 312,705,000. That's after 6 months. That's how many we've got. Then it dropped to 1.1% per week for another 6 months. So now we're going to take this amount here, and what we're going to do is take that value into the calculator, and we're going to, all right, so what should we say here? The next 6 months. And that's going to go to this figure here, 312,705, blah, blah, blah. Then that's going to be 1.0, what's this, 1.1%? So 1.011 to the power of 26. So I'll get the calculator out and we'll do that. I'll just show, just in case you're not doing this right. So we're just going to take that whole figure. So I'll just arrow up and select it. All right, that whole figure. And multiply that, hit the wrong button, multiply that by 1.03, get outside the bracket, raised to the power of 26, it's another 6 months. Oh, what am I doing, 1.03, that's wrong. It's 1.1%, isn't it? So it's 1.011 to the power of 26. Hit enter, and now that is our new figure. So I'm going to just take a little screenshot of that and transfer it across. Okay, so now we're at, what's this number here? If I break this up, 415.5 million. Now we've got a year at a 0.75% per week. So now that's going to be this amount here multiplied by 1.0075 to the power of, for the whole year, 52. So let's get into the calculator and do that. So the next 12 months, bringing us up to the end of 2010, took this figure here, dragged it into here, multiplied by 1.0075, right, and that figure there is 0.75% growth. 0.75, 0.0075 when you divide by 100, 52 being the number of weeks in a year. So this figure here represents how much is left at the end of, how many users there are at the end of 2010. So that's about 613 million and 608 million. So this is a much better model. So assuming this is a way to show that this model better describes. So that's That's roughly 613 million, which is roughly 608 million. So we could say that's a better model than the 3% per week, which was clearly way out. Cool. All right, part C. I'll have to get rid of example 27 here. Now, part C, we're taking this figure here, 926,982.179. We're taking that amount, and it's now, the rate of growth drops to 0.6% at the beginning of 2011 and remains steady, right? So that's just going to go on for n number of weeks until we reach 1 billion. 0.6%, right? Yep, 0.6% per week. So we're going to take this amount here, 612, 982, sorry, 982.179, blah, blah, blah. All right, we're going to multiply by 1.006, all right, because that's 0.6%, and that is going to be raised to the power of n. I'm not sure what that is, but we want to get to greater than 1 billion. That's a million, and that's a billion. So we're going to take this billion, divide it by this 612,000. So this is 612 million, and then we'll have 1.006 to the power of n is greater than this. So I'll just do a bit of work on that. Okay, so now we have divided both sides by this this monstrosity of a figure here, a million divided by this, and we get this figure. All right, so now it's 1.006 to the power of n is, we want it to be greater than this figure here. Now, what we could do is graph this, I guess. Graph y equals 1.006 to the power of x, and we could see at what point we get greater than this. That might be our best bet, seeing as we don't know, we haven't studied logs yet, because that would be our easiest algebraic method. Okay, just to explain, I have graphed two functions. This is not 1.01, it's rounded off. It was 1.006 to the power of x. That's this red exponential curve here. On the x-axis, we've gone to 100 here, and on the y-axis to 2, so you can see what the scale is. And I've graphed 1.63, which is the other side of my equation. If we go back to what we're looking at, so I've graphed y equals this on the left, and I've also graphed y equals this. What I'm looking for is the point of intersection. The point of intersection of the two graphs is over here. So let's find the point of intersection through menu, analyze graph, intersection. I'll go ahead and do that, and I can see if I pull that aside, it's 81.7. So how do I interpret that? 81.7. That means that when n equals 81.7, these are equal. But I want n needs to be a whole number, because it's a number of weeks. It's a discrete amount. So when n equals 82 will be the first n value for which this 1.006 to the power of n is greater than this. So therefore solving my original problem. So therefore reaches 1 billion users after 82 weeks. 82 weeks. So 82 weeks, what's that about? So we started 2011, so it would be sometime during 2012, about May 2012, roughly. About May 2012, and you can probably argue that I've got the wrong month there, but I'm just guessing 32 weeks. Oh, hang on, 30 weeks into 2012 is beyond halfway, isn't it? So maybe I'll revise that to July. Okay, but the important thing is that the maths is understood, and this 82 comes from an intersection of this equation with this straight line. I'm solving this. When we've used logs, we'll solve this algebraically, but at the moment we need to do it graphically. Okay, we're going to have a look at another example. Now, I believe that maths is best done by doing rather than by sort of watching and sitting watching this. I don't know. What I'd normally like you to do is to stop, go and do some questions. But in this particular work is best. I guess there are just some ideas and some methods, some strategies that it might be actually a good idea just to see play out, so that obviously we're going to go and do exercise 1D after this, and there's plenty of practice for us there. But before, I don't think, I would sit through this example, and then we'll go into 1D and have a look. So let's read through this, because I don't think going into this question you perhaps would be very sure about how it's going to play out. But it's quite a common type of question. Let's work through it. When Jacob turned 18, righto, lucky Jacob, access to the money his grandparents had invested in a savings account, he decided to reinvest 10,000. So he's got 10,000 when he turns 18. Compound interest of 3% each year. He decided to add $200 to this investment on his next birthday and each following birthday until he turned 25. Right. So when he turned 18, he got $10,000, and he decided to add $200 to this investment on his next birthday. So when he turned 18, when he turned at 18. All right. So let's just get this right. So at age 18, inherits $10,000. Okay, what happens then? He invested it at 3% a year, and he adds 2,000 on his next birthday. So, all right. So at age 19, let's say 1 year later, what's happened? His $10,000 has earned 3%. So that's it. 10,000. He's earned 3%. It's 3% per year, and it's gone for the year. So it's to the power of 1. He then adds $200. So that's how much he has at age 19. But that's not the question. The question is, what does he get when he turns 25? So we need to go and look at what happens in another year's time and start to look for a pattern. So let's have a look at another year at age 20. So when he turns 20, 1 year later, what's happened to this amount here? Well, this amount is earning 3%. So this 10,000, and I'm intentionally not, I don't want to figure for this because it would cloud for me what I'm looking for, the patterns I'm looking for. This amount here gets 3%. It earns 3% during this year from 19 to 20, right? So this amount, he's got that sitting there when he's 19. This figure here, he gets that at 19. That all goes in here. You see all that and earns this amount of interest. Okay, I'll just remove those little things. Earns that amount of interest, and then last thing he does before it goes into the following year is he adds another 200. So let's just tidy this up a bit. I can see a 1.03 needs to be distributed through this bracket. It also gets the treatment there, 1.03 by 200. Airplane motor's just gone on for some reason. And then I've got this plus 200 sitting on the end here. Now, I reckon I can just do a little bit more here. So let's just play this out one more spot, perhaps. Looks like I've got 200 as a common factor, doesn't it? Right, 1.03 plus 1. All right, does that look better? So there's my simplified version at age 20. Now, I want to do this for as long as it takes to understand what the pattern is. I'm not going to do it all the way through to 25. I reckon after one more year, I'll have it. At age 21, right, one more year. So we're going to take this whole amount here and give it the 3% treatment. So it's going to get 10,000, 1.03 squared, plus 200, 1.03, plus 1. All that gets the 1.03 compound interest, and then 200 more goes on. All right, remember that's the last thing that happens. So during this year, this is during the year, all that happens during the year, and then this is all right. That's the last thing that goes on. All right, that just gets whacked on top. So that's what we need to consider. So this amount here, he would take into his 22nd year, etc. Right. Once we've simplified all this, we should see a nice little pattern emerging. So this 1.03 needs to be distributed. It gets multiplied by this 10,000 1.03 squared to become 1.03 cubed. Nice. Now what happens in here? All right, well, firstly, I've got 200 times 1.03 squared now. So I've got 200 by 1.03 squared. All right, now this is 200 by 1.03. So I've got a 200 by 1.03, if you see how that distributed out. And then I've just got that 200 on the end. Now, if I rewrite that with 200 as a common factor coming out, what do I see inside? I see 1.03 squared plus 1.03 plus 1. Okay, let's hold there. Because let's just observe what we've got. This looks pretty straightforward here. This looks like what we're going to do is this is just going to climb by one each year. That's going to become 4 at age 22 and 5 at age 23. So we can project there. Look at this. Right? Now I had 200. If you looked at the year before, I had a 200 out the front. So that looks common. That looks steady. And here I've got 1.03 plus 1. Here I've got 1.03 squared plus 1.03 plus 1. Now what I want to concentrate. So 200 looks solid. This looks solid. But in green, what is this? Does this look familiar? Does this look like something? Or maybe if I reverse the order, 1 plus 1.03 plus 1.03 squared. Does this look like it might be a geometric series emerging? Well, it is, isn't it? We've got a U1 of 1 and an R of 1.03. So this is where, oh man. This is why this is sitting in at this stage of the course, because here's our geometric series that's emerged. All right, so we're going to project now to at age 25, because that's what we want. We want to know how much he is going to collect at age 25. Okay, so let's see. What do you think? Let's work it through. We'll just project through to age 25. It's another 4 years on, so that 3 is going to become 1.03 to the power of 7, would you say? If you like, I quite like to look at the difference between this number and this number here. So 21 minus 3 is 18. So 25 minus 7 is 18. 20 minus 2 is 18. They're the patterns I'm looking for. Okay, I know that I've got a 200 here. What am I going to have? I'm going to have 1.03. Now, what's this power? It's 1 less than this one. So it's going to be 6 plus 1.03. And the powers are going to go down. I can assume all the way down to 1 being my last term. Okay, so it's crunch time. It's ready to go. This is easy. I just whack that into the calculator. This needs a little bit of work. Okay, because this here is a GP, a geometric progression, which has U1 equaling 1. I'm going to look at it in reverse. I could say that's U1 there, but then I'm looking at a value of R that's 1.03 to the negative 1. I don't want that. I want R to be equal to 1.03. Just looking at it from right to left. And the number of terms, what is it? 6 down to 1. It's 7 terms, isn't it? So my sum of 7 terms here is going to be U1, which is 1, by R, which is 1.03, to the power of N, which is 7, minus 1 over R minus 1, 1.03 minus 1. So this here, let's give that a little border. That there is the sum of what's inside the bracket here. So I am going to rewrite this as 10,000 by 1.03 to the power of 7 plus 200 by 1.03 to the power of 7 minus 1. Just simplifying what I've got here, 1.03 minus 1, that's just 0.03. This is my total. Now you can see at age 25, that's not so many years, but if it was 35 or 45, this becomes a really, really useful a useful observation that inside the brackets here, wow, look at that. That is a geometric sum, and I have a shortcut way of tallying that. So put this through the calculator. Okay, so we're just about there. That's gone through the calculator, and we get this figure here, 13,831.23. This is a monetary figure. That's the amount he's going to pull down at the age of 25. Not the question though, is it? I don't think. Evaluate how much money was in his account just after his 25th birthday. Good. Evaluate the total interest gained over this time. So that's the amount. So therefore, collects or has $13,831.23 after or when he turns 25. Now the amount of interest that's earned, let's separate the amount of interest. So contributions, this amount here is made up of contributions and interest. All right, so the contributions have been 10,000. That was the initial amount. And then there have been 7 lots of $200 that have been put in. So that's 1,400 plus 10,000, which is 11,400. So they're the contributions. So the interest is the difference between these two figures here. So that would be 13,831.23, 13,831.23, subtract 11,400, and that figure is to the nearest dollar, 2,431 in interest. Right, that's the end of the lesson. I'll see you in class.